Hello?
Oh, hello?
Hello.
Hello?
I hear you. Actually, my other camera is better than this one.
Professor, did you post a lecture for
No,
Tuesday?
I didn't. I wasn't able to do it this week, unfortunately.
Okay.
Posted little segments here and there. We'll make up the time. I'll see what I can do this weekend. But we'll make up the time. All right. Welcome back. We'll make up Tuesday's lecture throughout the course, or I might post some videos this weekend, depending on how much time we have. So the first test will be, we'll make it July 2nd. Okay. So in 2 weeks, we'll have the first test. And hopefully it'll be up to chapter 7 or 8, depending on how far we get in the next 2 weeks. So, and then the test will consist of 3 parts: an hour short answers, where you'll be answering questions from Master in Physics for 1 hour, and then we're going to do an oral part of the exam, where I meet individually, one-on-one, and I ask you some questions regarding take-home problems that I will give out. I'll give out 2 long answer take-home problems that you will have to have done, completed 1 day prior to the test. I'll hand them out next week, and then and those oral questions will pertain to those questions. I can ask stuff outside of those questions that are conceptual questions that are related to the problem, but aren't specifically asked in the problem. So it could cover any topic that's related to the problem. So it's not just those set of questions. I won't just go in depth, but I could ask you something that's related to the concepts involved in that problem. So, and I find it very useful. So when you're studying for it, think about the questions I will ask. Okay, so how will I look at this problem? What are interesting characteristics of this problem? And then you'll come up with some questions yourself, and you should find the answers to it. And that's a good way of studying for such a test. So you usually do 4 questions. That takes about 5 minutes. So it'll be around 4 questions, and that will take up the rest of the lecture time of the class. Okay. Let me get my book out. So today's topic will be on Newton's laws of motion. So we'll cover that. I want to do this chapter quickly. There's very, very important concepts in here that we have to iron out, but generally the mathematics involved in this section are not terribly hard. Kinematics is definitely tougher, but the concepts here are very important to know. Okay, so what is a force, right? So you could say that a force is anything that causes an acceleration. Okay. Now, this isn't the complete description of a force, right? So the complete description of a force is much more than just saying that the force causes acceleration. But one of the end results of this is that forces are proportional to the acceleration that an object feels. And I should say the net force on something. And this goes into Newton's first law of motion. So Newton's first law of motion states that every object will continue in either a state of rest or a uniform velocity as long as there's no net force on it. So, and this is a big difference between a state of rest, right? So in the ancient times, I think it was Socrates, but they believed that the natural motion of every object is to be at rest, right? So that means that if you're moving, right, and there's no net force exerted on you, you will naturally tend to slow down and stop moving, right? And in our everyday world, that is a very common, very easy way of looking at the world. It's very common, right? This is because of frictional forces and drag forces. So there tends to be other forces that are proportional to, that are related to the object's motion that tends to slow it down, like wind resistance. But it wasn't until Galileo's genius came along and said, no, hold on. If we remove these other forces, like wind resistance or friction, the object will continue moving along until there's another net force acting upon it. So now this states that the natural motion for an object is to stay in motion until there's another force acting on it, right? So this is one of the assumptions that physics is based off of, this idea of inertia. Inertia is the idea of something tending to stay in that state without anything applied to it. So it has a certain inertia to it, right? Now this is known as the law of inertia, and it's very different than just objects wanting to stay at rest, right? Objects want to stay at a uniform velocity unless there's a force acting on it, and this force is proportional to the acceleration. Now we come into this other quantity that we call mass, right? And it's a measure of a quantity of matter, right? It's how much matter you have in here, right? And it just so happens that this mass that we normally think of is related to inertia. So depending on how much mass it has, it will tend to want to stay in motion proportional to how much stuff there is. So, so then what happens is that for two objects going at the same velocity, if one's larger than the other, the larger one will want will want to stay in motion, will take more force to change its to change its velocity or to give it some kind of acceleration. So it requires more force. And in general, this will lead us to Newton's second law of motion. And this states that an object's acceleration is directly proportional to the net force. So Newton's second law states that the force, the net force, where force is a vector, is equal to the mass times the acceleration. So the acceleration is proportional to the force, right? And vice versa. So the force is equal to its mass times acceleration, right? And this mass represents how much inertia, how much force it takes to accelerate it a certain amount, right? And the units here, the SI unit for mass is kilograms. So the units are kilograms meters over second squared, right? So acceleration is meters over second squared, and then we just multiply it by kilograms. And this is known as a Newton. This quantity is a Newton. Let me write this like this. Okay? That's what we call Newtons. Right? Now, this is a vector quantity, so if we have multiple forces, we would have to add up the components like we did with the velocities to get a net force. Now you have to realize this, right? So what is this saying? So if I push on an object going this way, and there's another force pushing on it going upwards, let's say, it would move like this, right? And if you think about it, this object can only move in one direction. It can only feel one acceleration at a time. Otherwise, or one acceleration, in one direction at a time. Otherwise, it doesn't make sense, right? You can't have an object accelerating in two different directions, right? You can break it down into components, but the overall acceleration will always be in one direction. Otherwise, the object is coming apart, literally, right? So it's unphysical to say that there's two acceleration vectors, right? An object, solid object can only move, therefore accelerate in one direction. So, and this is saying that the net force will, the sum of all the forces on a system will accelerate in this direction. Now, like I said, this equation doesn't fully describe a force. Newton's second law just says that the net forces cause an acceleration. That's all it says. So we don't know anything more about any of these forces involved in this problem other than it causes an acceleration. And we'll go into details and analyze it later. Now there's different types of forces, which we'll go into. But let's first study properties, right? So then these forces can be broken down into its components, right? the x component is equal to the acceleration in the x direction, right? Same goes for the forces in the y and the forces in the z. Right. And then we can write this force vector using our unit vectors. So we'll have Fx. This is the sum of the forces over here. Fy in the j direction and z in the k hat direction. All right, and this is what we use to describe the forces. And all we have to do to calculate the equations of motion is just solve this equation, Newton's second law. And then we can figure out the acceleration, and we're given the initial conditions, how fast is the object initially moving, and where is its position. We could fully describe most motion using this formula. Actually, all motion, but some problems are more difficult and require more advanced techniques. But this fully describes motion in everyday life. Any questions so far? So let's do a simple problem. Okay. So let's do this in one dimension. So let's say if I have a car and I need it to, and we want the car to, for safety standards, to brake from 100 kilometers an hour in a distance of 55 meters. So we have a car. Right? And it's initially going, we'll call this X, is 100 kilometers an hour. Right? And then when it gets, we want it to go down to 0 at 55 meters. So I'm writing out and drawing the problem. And V is equal to 0, right? And then what force do I need to apply to this car for this to occur? What is the force, right? So we're working in one dimension, so we don't need to use vector analysis. So we can just write it like this. So the force is equal to ma. Now we're given the size of the car, and the car, the weight of the mass of the car is 1,500 kilograms. It's the mass of the car. And so we have the mass. We just need this, right? So if we look at it, this equation, we have two unknowns, right? Of course, we don't know the force, and we don't know the acceleration. So that means we need another equation, right? And we'll go to our kinematic toolbox. So from our kinematic toolbox, what equations do we want to use? All right. So one equation is this. All right. And another equation is this. right? And then I could give the velocity as this, right? And we'll assume that, and we're looking for the net average force again. So what equation do we want to use, right? We don't know T over here, and this is a polynomial that's more difficult to solve. So we'll look for the answer elsewhere. Well, let's look at the second one. We know V final, that's 0. We know V initial, it's given to us. We don't know the acceleration, and we know the distance. So we could use the second one to solve for it. So that's what we'll do. We'll use this equation to solve for it, because we know everything about this equation except for A. So that's the only thing we need, right? So let's use this equation. And we'll solve for A. Right. And now we'll just plug in the values for this. So 100 kilometers an hour comes out to be 28 meters per second. All right. And where do we get this from? So when we convert 100 kilometers, so I'll write it over here. So we'll, from a dimension analysis, we want to convert this into seconds and meters. So let's do kilometers. So there's 1,000 meters per kilometer. So 1,000 meters per kilometer. So meters per kilometers, per means divide, right? For each one. There's 1,000 meters per kilometer. Okay, this converts to meters because the kilometers cancel out. Then we have to go from hours to minutes to seconds. So in 1 hour, there's 60 minutes. So there's 1/60th of an hour per minute, right? And then there's 1/60th of a minute per second. And then when we do this math, it'll come out to okay. So now we have that. So 0, the V final is 0, so we just have this, right, meters squared over here, over x minus x naught. We'll choose x naught to be 0. X, we can make x 55, right? So then it's just divided, 2 divided by 2 times 55 is 110, right? Meters, right? And then if we look, the units will work out right now, right? Meters divided by meters squared, and then we're left with, oh, this should be seconds. We're left with meters over seconds squared. So this works out. And we get the acceleration as negative this distance, right? Because of this negative sign. Add that in. And that's the acceleration, negative 7 meters per second squared. Now we can plug this back into here, and we get our force. So the force is equal to 1,500 kilograms times 7 meters minus 7. And we're left with And we're left with this quantity here, and negative sign. And then we can convert it to newtons. So, and I'll put it in scientific notation, times 10 to the fourth newtons. So this is how many newtons we have to apply to stop this car in this given amount of distance. Now, we don't really understand what newtons are because we work on the English system, unless you come from another area of the world. But we use the system pounds. Now, you normally think of weight in pounds, and weight is a force. It's the acceleration due to gravity times your mass, right? And the relationship between newtons and pounds is pull up my definition. Had it. Got it. So 1 pound of force is equal to 4.45 newtons. So if you hold a gallon of water, that's 8 pounds, right? So that's a little less than 2 newtons. So to give you an idea. And this, the force required to stop a car is 4 orders of magnitude more, right? So just to give you an idea of how much force it takes to stop a car, you know, it's a little less than 10,000 times more force than it is to hold a gallon of water. Okay, and generally this is how we'll do Newton's second law, and we'll do a lot more of these problems. So first I want to talk about Newton's third law of motion. So Newton's third law of motion is probably the most familiar, I think. And it says that when one object exerts a force on the second object, the second exerts an equal and opposite force, exerts an equal and opposite force than the first. So that means, let's erase this. So that means, let's say if I'm on the ground and I'm pushing a box, let's say I'm struggling pushing the box, I'm moving it backwards like this, right? The force exerted by me on the object, right? So the force exerted by me is F1, right? Let's say me as, okay, FPM, right? This is, the notation is a force exerted by the person on the mass. So the first subscript describes the thing that's creating the force. And then the second one is what the object, what's experiencing the force, right? And then this is equal and opposite to a force exerted on me by the object. So this is, let me get another marker. You guys see that? Yes, okay. So this is the force exerted on me by the mass. So the mass on the person, right? And it happens by Newton's third law. These two are equal to each other. Equal and opposite. Right? Now let's think about it. Does this make sense? Right? Well, if there's always an equal and opposite force, why do we get acceleration, right? Shouldn't they cancel out? Right? Because it's the net force that moves. Now, what's wrong with this line of thinking? Anybody? So if there's an equal and opposite force, why do things move? Right? Why don't they just cancel out? Well, the answer to that is that these two forces are exerted on different objects. This force is exerted on the block, and this force force MP is exerted on the person. So that means that if we were in space where it's just me and the block, if I push the block, I would cause it to accelerate that way, but then I would also accelerate or the block would accelerate myself in the opposite direction, right? And we'd move apart, right? Now, this is true with anything. So why don't we move apart here? The reason why we push if we push on the block, and yes, you had a question?
Is it because of friction?
Exactly. It's exactly due to friction. So when we push on the block, we also have a force. Well, there's a frictional force on the mass. But let's assume the bottom of this mass is frictionless for now, and the only friction with the surface comes from my feet. So now we're exerting a force on the ground, right? So we're pushing on the block, right? Or we're pushing backwards. Let's say I'm pushing it this way, right? I'm pushing the block that way, right? There's an equal and opposite force this way. That means that my feet apply a force on the ground with a force this way. Let's say F person, I'm applying the force to the ground, and it's applied on the ground. PG, we'll call it, FPG. Then there's the force applied on me by the ground is in the opposite direction, which is which is of course, when we follow the logic, is the opposite to MFP. All right. So this force is equal to, it's on the ground by me, right? On me. So this is the force applied by the ground on the person, right? And this force cancels each other out, right? So if there was no friction, it would be impossible for us to move the box, move both of us forward at the same time. We need this other force that's connecting us to the ground to resist the reactionary force when we push on the block. Now, if you look, these forces can get kind of complicated, right? In the end, these two forces will cancel each other out, and we'll just get a net acceleration that way. But we have to analyze the problem for all these forces, complementary forces that cancel each other out. We have to take into account this. And usually, the way we draw these forces is that we don't draw these forces in different places on the object. We draw it at the same location. So if I wanted to draw the forces on this person, let me erase it. We draw it from one region, from one origin, one area. So let's say if we draw the forces on this person, we would mark out the center and we'll draw it all at the same location. So we'll have a force this way, which is from the ground, FGP, and then we have a force this way, MP by the person, right? And then on the block, we just draw it over here, we draw a dot, and then we draw all the forces associated with that person, right? Now, with the box, with that object. Now, we didn't draw all the forces because we only did it in one direction. So now, there's other forces involved here as well, right? Namely gravity. And then you got to realize that we're not accelerating in any vertical direction when we're standing on something or a box is resting on something, right? We're not actually accelerating. So that means there's another force that cancels out the acceleration due to gravity, right? And this is the force exerted on the ground. So let's get rid of the person. So if we have a block, right, we have acceleration due to gravity, downwards. We'll call this FG. We assume that it has negligible effects on the Earth. That's why we just label it with a G. We don't consider the complementary force on the ground because the Earth is so large. So we'll just call that FG for force due to gravity. Now there's an equal and opposite force caused by the ground since it's resting on it. And this is upwards, and we'll call this the normal force. Now, why do we call this the normal force? The reason why we call this the normal force is because this force, so any force that you contact another object with, right? So me pushing my hand on the board, right? You can't see it, but I'm actually pushing on the board. I could feel the force, right? My hand's not accelerating, so that means that there's an equal and opposite force that's pushing back on my hand. That's coming from the wall, right? And any of these forces associated with the surface, this force that's pushing back on my hand is associated with the surface of the board. And this force will always be normal to the surface. What do I mean by normal? It occurs at a 90-degree angle. So if I have a surface, the normal force is always perpendicular